just, as I was saying here, it's just minimizing the distance, not with respect to the square of residuals, but just in terms of absolute values. So in the case of quantum regression, what we are interested in is to know not how much certain characteristic X shift the average on Y, but we want to know how certain characteristics X shift the conditional quantile of Y. Now, let's see what we mean by quantile. A quantile, percentile, it's pretty much the same idea. Okay, so the formal definition of quantile, we say that quantile goes from 0 to 1, right? So if you call it percentile, you're going to go from 0 to 100, but to be simpler, we go from 0 to 1. Then that quantile of tau is the tau quantile of Y, the probability of Y being smaller than Q of tau is larger or equal than tau, and vice versa. Okay, so the quantile is pretty much the opposite of the cumulative distribution function. And so if you take cumulative distribution function here, you know that's what we are doing generally is to say I want to know the value of Y such that I have 40% observation to my left. It's smaller than that. So then I know that if I look at 0.4, I just go on the function and I know what is the correspondent value for that probability. Now, the median is going to be the one that is 0.5. Now the quantile is pretty much the opposite, right? So I want to say tau be 0.4 and I got exactly the same value. So it's the same idea of percentile and so on. So tau is telling us what percentage of observation we have lower than a certain value. Okay, so if I say the 0.4 quantile is, let's say, 1 for simplicity, then that means that in that variable, 40% of observation are smaller than 1. Okay, it's the idea of distribution distribution as compared to average. Now, there's no need to know this, you can revise yourself, but quantiles can be easily estimated. They can be estimated with a function that is called the check function. They can be estimated with this problem here. Okay, so the quantile, which is a median of Y, so the median of Y can be estimated as the minimization problem of this function. It's the check function in Y minus. So no need for you to know this stuff. But the check function, which gives us the quantiles of a distribution, has this shape. Okay, recognize that this is, for example, the check function that finds the 75th, the 0.75 quantile or the 75th percentile, has this shape. So similar to the least absolute deviation figure, which was here, this one. Notice that this doesn't have a closed form solution. It doesn't have a closed form solution because it has a point where you cannot find the derivative. It's obviously this point. But it turns out that this function just has very similar shape as the one of the least absolute deviation, but it's just that you use an asymmetric punishment for distance from the point. Right? So we have so far seen 3 cases. So OLS uses symmetric and squares. So the further you go away, the more is punished the distance. You got least absolute deviation, which is symmetric linear. So the more you go further away, you always get the same type of punishment. And you got this case where punishment is linear, but it's asymmetric. Okay, so one side will be punished more than the other. So these are three problems. These are the three problems we have seen so far. So OLS, which minimize the square of residuals, least absolute deviation, which minimize the absolute value of the residuals, and the quantile regression. It will minimize the quantile of the residual. Notice that the shapes of these problems are all different, but they all in practice try to solve something similar. We take a distance between what I want to estimate, what I want to predict, y, and some estimate, and I apply one function, and I have different functions. Now notice that this is differentiable, this is not differentiable, this is not differentiable, meaning that the first one, which gives us a closed form solution, what we call linear, the second and the third will not give us a closed form solution. And so this point will need to be found not through a formula, but through numerical methods. Okay, so what is the quantile regression in practice doing? Okay. So quantile regression is very similar to OLS. And so it's assuming that the quantile y conditional on x is a linear function. So you have alpha plus x beta. Now why is tau here? Because every problem will give me a different tau. As I said, OLS will be modeling the average, there's only one. Right? So the conditional, the least absolute deviation looking at the median, there's only one. In this case, I have all possible tau. So every tau, so if I want to say, if I want to model the 0.1 tau quantile, then it will have a problem. If I want to model the median, it will have a different model, and so on. Because we are looking at different parts of the distribution. Now, this problem here, notice that can be written like this. It's the way to solve for the quantile using the check function, so no need to know. Yes?
So, depending on the quantile you have, the intercept is going to change and the slope is going to change, but also the type of asymmetry is going to change between negative and positive.
Yes.
Okay.
So, every time I change the tau,
the slopes are going to change, no?
this change the problem.
Okay.
So I might be interested to look at, for example, if y is wage and x is education as usual, I might be interested in people which are relatively poorer, the effect of educational wage for those that are poorer. So I want to look at the lower quantile. Then that is gonna look at very steep on this side and very flat on the other side. In this case, I want to think about how does x influence y at the highest part of the distribution. Then my problem will become like this. But what I'm saying is that tau is between 0 and 1, which means that it's a continuous number, which means that I can write infinite problems if I want. So I can tell my software, give me the quantile regression for tau equals 0.1, 1, 2, 3, 4. And obviously this is going to change a little bit of this and giving me different minimization problem. So how do we interpret this? This is an example of quantile regression. So that's what quantile regression is. The red line is the average. Okay, so it's the OLS. The OLS, again, is telling us how does x, in this case is a simple example with y and x, okay, so one regressor only. So it's telling us how the average of y, conditional on x change, but x change. This is the red line. Now, the orange line is the quantile regression for q equal to 0.9. So this is telling us how x influences y for those in the higher parts of the distribution. Okay, so if y is wage, it's going to be the effect of x on y at the higher parts of the distribution, in particular for the 90th percentile of y. The same is true for 0.01. Okay, so this is the effect of x and y for the 0.1 quantile, or for the 10 percentile, in the lower parts of the distribution. So that means that potentially there are different effects of x and y along different parts of the distribution of y, where coelastic tells us the mean, but not necessarily is the median. That might not be the same. While the others are telling us about other quantities. So what do we learn from this? This figure is telling us that if you are on average, the average effect is positive. Now, if you are in the lower parts of the distribution, obviously it shifts down. Because on average, people will have lower wage, and it gets flatter. That means that the effect of x and y is flatter at the lower parts of the distribution. And in this case, it's steeper at the higher parts of the distribution. So these regressions are telling us something about whether we expect the effects to be constant along different parts of the distribution. So whether x affects the quantiles in a different way, or whether we expect it to be constant. Now, as I was saying, quantile is going from 0 to 1, so I can potentially draw hundreds, thousands of these lines every time changing a little bit tau. So generally, software presents outputs in this way. So softwares allow you to say how many quantiles you want to study, but if not, there are already commands implemented that are going to split into a standard number of quantiles. So in this case, you see that you have a quantile here, and here is the marginal effect. Okay? So if you have only 1x, then this is going to be the slope of these lines. Is the coefficient, therefore is the derivative. So what is this telling us? This is telling us generally the line is the OLS, confidence interval on the OLS, and each of these points are quantile regression. So what do we learn from this? What do we learn from this figure? See, so the OLS is giving you pretty much the derivative of 0.10, partial effect 0.10. So if x increased by 1, the average of y increased by 0.10. But what is in addition to?
Increasing.
What does it mean increasing in this case?
The more x, the more effect we have some. I mean, the higher the quantile, like the proportion, the higher the effect.
Okay.
No, sorry. Just basically that if like the OLS show us a linear relationship, well actually the quantile is not a fixed relationship between all the elements. That some elements are gonna have, like, on some parts the impact is higher, on some parts the change is lower, but it's not just.
Remember, this is correct, but remember that in some parts, when you say in some parts of the distribution, it refers to the distribution of y.
Yeah.
Okay? So this means that the effects is overall on the average is positive. It means if I increase x, the average of y will increase. Now, why is that increasing that average? Remember that the average is pushed by what's happening in other parts of the distribution. And so it can be that the whole distribution is moving. It can be that one part of the distribution is moving more than one, than the other one. Or it can be that one is unaffected and the other parts of the distribution change. So this figure here is telling us that the whole distribution is changing, but some parts are changing more than other parts. Okay, so that effect is driven by those that are in the higher parts of the distribution of y that change more with respect to x, as compared to those that are in the lower parts of the distribution. Notice that this is indicative, the fact that these effects here is statistically different from the effect on the average, which means that these parts of the distribution, these quantiles, is really telling us that the effect is statistically different, and the effect of x on y, it is much smaller than the one at the higher part. Okay, so if you are a policymaker and you have to make a decision based on this, obviously this is telling you that people that are on the higher parts of the distribution of y, they respond more to x. Okay, so if x is education and y is wage, then you know that wage is more responsive for those that have more wage as compared to those that have no wage.
Can you identify like outliers with the quantile regression? If you don't have like a straight line, we have different.
No, the quantile regression is not really giving you outliers, but it could potentially be telling you about outliers in y, right? So not in x, in the distribution of wage. So outliers are generally, say that this is your regression, right? So outliers are people that are here or here, very far away from that. This is not really telling you to distinguish this from this one, but it's telling you for sure that people that are going to be here are going to be estimating the relationship that are around here, right? So if this is if these are the points, with a lot of dispersion, right? So the OLS will be just making everything happy, right? So it's minimizing the square of the sum of the square root residuals. While quantile will be trying to estimate the relationship in this one at high quantiles and with this one at low quantiles, knowing that if I am in a very low quantile, right, so if I have an outlier, obviously this outlier will be picking up on the very low quantiles of the distribution. So it will be trying to tell me the relationship around here or the relationship around there. But remember that if I have one outlier and I'm looking at the 10 percentile of this distribution, then this will be just one. Then 10 will include also this one. The main difference it's important to notice that this methodology does not split the sample. So what we are doing is we are using all points, but we're using all points to estimate quantiles. It's particularly important to do that. So this doesn't split the sample into, we can split the sample into different quantiles of the distribution of y and estimating in the part. That's not what we are doing. So what we are doing is to use the full set of data to estimate the relationship in a particular quantile. Now, what is this figure telling us about effects on the median of y? Yes. Okay, so this is a case in which we're going back here. Right, so we asked, does the OLS consistently estimate theta when we were interested into the median? Okay, so we said that we needed to impose some additional assumption, some sort of symmetry. In this case, we see that the effect, the quantile effects for 0.5, which is the median, is exactly the same as the OLS. So that means that the relationship is such that our data most probably has some of these features. Okay, so some symmetry features such that our data, once I add controls, all controls, the effect on the average is pretty much the same as the effect on the median, which most probably we know is because average and median are going to be pretty much around the same point, which also means that most probably our distribution, our underlying distribution in this case, is symmetric. That's what we learned from this. Okay, so this is an example of nonlinear models. It has some applications. It allows you to study a bit more relationships on quantiles rather than averages. And as I said, it's the first example of nonlinear. Nonlinear because this doesn't have closed form solutions, which means that if you're going to go on the software and run quantum regression, you will see that the software is iterating. It's not just spitting out a result like a linear regression.
Okay.
Yes.
Question. Those slides are the ones uploaded?
Say that?
Are those slides the ones uploaded?
I don't know. You mean these ones? Yeah, they should be. Okay, second case. As I said, the first case are those where, first case of nonlinear models are those where I'm interested into estimating the conditional features of the distribution, and those do not have closed form solution. Now, a second one is a different case. Okay, so it's a case in which I am interested into the conditional mean, I'm the same way interested into this. But the way I deal with it is that instead of assuming it's a linear function, I assume it's a nonlinear function. And we call this nonlinear response. So notice here that I'm not assuming anything about that relationship. So I am assuming that M is a whatever function of x and theta, but is not linear. Doesn't have to be linear. So what I can do in this case? So I know what ULS is doing, therefore I can do exactly the same thing. Okay, so I minimize the square of residuals. But in this case, I might not have a linear, a closed form solution, because I don't know what is inside here. Imagine that inside of M is an exponential function, as an example. It can be whatever you want here. It's an exponential function, then you cannot really find a minimum in that case. So how do we deal with that? Generally, and we will have to go a little bit faster on this part. It's a bit more advanced in math, but I want you to just take the intuition. If you are interested into this type of problem, which is the same as ULS, when M is, so Mx theta is x theta, right? So it's a linear function. Then we are back in ULS. But if it's not like this, it's something different, it can be whatever function, then we are in a different problem. Now, an important features of this model that we want is we want to have a unique solution. And this, as we will see, is particularly important when we look at the maximum likelihoods. So this is an important feature. We want to have, in this problem, we need to impose in that problem that there is a unique solution. Why do you want that? Why do you think we want that? Any idea? Why we need a unique solution? Because if you have to make a decision, Yes. How can you interpret a model that gives you an x that is positive and an x that is negative? So how can you say, well, you know, what is the effect of x on y? You say, well, it depends. It is both positive and negative, or it is small and large. And so you cannot say that. So you cannot have a model that is such that we get multiple solutions. Okay, so that means mathematically the way it's written is that there is only one that is equal to 0. Okay, so for all other combination of parameters, this is going to be positive. It means that there is only one meaning. It's a unique solution. This is why sometimes in these more complex models, we have what is called the parameter space. Why do we need a parameter space? As simple as that. Okay, so if we have potentially many solutions, so the way to get back to one solution is to impose some restrictions. In the example of before, so imagine that your problem gives you two values of x, one positive and one negative. But your model, or your underlying economic model, tells you that x can only be positive. Which means that if I impose parameter space of x being positive, then I don't have two solutions, I have only one solution. Because the other one is discarded by the parameter space. So it's outside the parameter space, therefore doesn't apply. Now, you get the proof here, and we already discussed that last time. The rank condition in the OLS, it's pretty much this condition here. It assumes that I have a unique solution. Right? So we saw that in the simplest case, which is alpha plus beta x plus epsilon. Right? So we have shown that this beta is equal to the covariance between y and x divided by the variance of x. Right? And we saw last time that the rank condition is such that this is larger than 0. That's what we showed last time. Now remember that this, apart from being the rank condition, the no particular linearity assumption, is such that this has a unique solution. Because if this is 0, eta has infinite solution. Okay, so it's a way to impose this very simple assumption. It's the same, it's not the way, but it's exactly the same assumption of imposing to have a unique solution. Remember that in the more complex case, when I have x beta, right, so many x's and many betas, the rank condition is such that I have exactly the same number of equations as the number of unknowns. When I write beta equal x prime x, expected value of x prime y. Okay, so the rank condition tells me that if I have k betas, here I'm going to have k equations. Same number of equations with the number of unknowns. It's exactly the same of this more general assumption, that I'm going to have a unique solution. This leads us to the M estimation principle. So you've seen that we have many estimators that are doing exactly the same. We saw them here. These are just some examples, right? This is minimizing the square of residuals. This is minimizing the absolute value. This is minimizing the check function, which is picking up the point value. So we call all of these estimators M estimators, or M estimation principle. So we're going to have, and notice that we're going to see other cases of this, but the general idea is that we will be minimizing function. And this is the closest mathematical interpretation of what we're doing. We will be minimizing a function where that function is containing two elements. Some is data, and some are parameters. But we will always be doing that. Okay? So we'll take a function that is a mix of data and parameters, and we want to minimize that. This is going to be consistent because these are minimizing an expected value, If you minimize an expected value, it means that when you're minimizing the sample of this, it's going to converge to that one. And the only real assumption that we need is to have a unique solution. Okay, so that the unique solution exists. So together with this idea, we put together the ULS. Right? So the ULS assumption is orthogonality plus no perfect collinearity. So those two assumptions make sure that the ULS has one unique solution. That only one unique solution exists to that problem. We're not going to go through this, but just for you to get intuition, if you're interested, is that because we know this is a minimization problem, how do we solve? We go back to high school. How do you deal with the minimization problem? What do you do? Huh? Yes, well, you start with first order conditions, first derivatives, right? The first derivatives are going to tell you, first derivative is equal to 0. I'm going to tell you where is the minimum or the maximum. Then what do you do? From first derivatives,
Take the second.
second derivatives, which tells you the curvature of your function, whether I'm in a maximum or a minimum, whether I'm in a local maximum or a local minimum. Right? So the function is looking like this, right? So I'm going to have two solutions in this function. I'm going to have a maximum and a minimum, right? But only one will be a minimum. And the second derivatives are telling us the curvature in this point. So it's telling us that the function is going down and then going up. Now remember that if I have, so in this case, I'm going to have two parameters to estimate. Right? So in the OLS version of this problem, I'm going to have two first order conditions. So the first order will be with respect to alpha, the second with respect to beta. Now, if you move to second derivatives, how many derivatives you can have? 4. Because you're going to have cross derivatives. Right? So, if you don't remember this, or especially in this case, the score, we generally refer as a score, is going to be a vector or first derivatives of the problem. The Hessian is the matrix that contains second derivatives. Now, it can be shown what we've seen yesterday, the asymptotic distribution of OLS can be generalized to all M estimators. And it turns out that that asymptotic distribution, and we don't have to go through it, but that asymptotic distribution is a function of two elements, first and second derivatives. Okay, so if we're going back to the OLS problem, just to give you a quick intuition of this. So yesterday we looked at the OLS, the other day we looked at OLS as more as a starting from, let's look at the simple case. Starting from this and trying to find a way to identify beta. But today we've seen that this problem is exactly the same as minimizing with respect to alpha and beta. The expected value of y minus alpha minus x beta. So identification arises from first order condition, which means that in this case the score will be, how do you call the function here? We didn't give a name. So the minimization of this. So the first one will be the derivative, calling A with respect to alpha, and the second one is A with respect to beta. So notice that this is the score, first order condition. We want this to be equal to 0. You're going to have two unknowns. Two unknowns, two equations. Now notice that if I am interested in a minimum, this needs to be 0, which means that the score will be equal to 0. This, as the name, is called Fisher consistency. Now, the second derivatives will be the Sn, derivative of A with respect to the alpha and alpha, derivative to A with respect to beta and beta, and here we have derivative of A with respect to alpha and beta, which is the derivative of A, beta, alpha. Okay, so 4 factors. Now, everything we derived yesterday about the standard errors of ULS turns out that they also have a mathematical relationship with this minimization problem. And don't need to know it, but the asymptotic distribution of my estimator will be a function of something that has to do with the Sn, second derivatives, in the denominator, because -1, and something that has to do with the square, first derivatives. This is exactly what we have derived yesterday. So this is telling us that if we are in a bigger problem, okay, so we are thinking about bigger problems, all of these problems are going to behave exactly the same way. So we will be minimizing a problem, generally a distance, and all of those, their precision is given by how first and second derivatives behave. So the idea of precision is not just a statistical one, but is one that is telling us something about this minimization problem, okay? About curvature of the objective function. Now, why is this important? Because if my problem is this one, and there are many of these problems, then all I need to know in order to compute the estimates and to compute the precision is to know how to compute first and second derivatives. That's all I have to know in order to build all I know about a large number of estimators. So if you don't know statistical theory, but you know how to compute derivatives, then you can find the robust sandwich estimator for the standard errors of ULS. It's exactly the same type of estimator. So let's say in the last few minutes, we introduce a different approach that is related to error estimate, which is another example that goes very far away, not completely far away, but it's more general than ULS, which is the maximum likelihood approach. So the maximum likelihood approach is telling us the following. We have some data, and we don't know what this data is, where it is coming from. Like this one. Right? So we plot density, so in this case it's an Instagram, and we don't know where this data is coming from. But we want to compute the underlying distribution of this. So we've seen non-parametrically we can estimate density. Density graphically will just make this histogram continuous and look like this continuous, without assuming anything. But for some reasons, we might want to estimate the underlying distribution. In this case, this data is coming from a normal distribution. It's been extracted from a normal distribution with an average 0 and some positive variance. So if I want to replicate this sample, or I want to study this data, then I might want to know what are the parameters of that normal distribution. But if I want to know that, step one is to assume this is coming from a normal distribution. Okay, so we know because that's what we are applying every time you compute an average and a variance. So when you compute average and variance, you are applying pretty much this. We know that if you're interested into this distribution, then all you need to know is the average and the variance. So if you compute average and variance, then that's all you need to know, because you have a formula of a normal distribution. It has some parameters, and it takes in averages and standard and variance, and it will be following this distribution. Now, it turns out that's a simpler case. What about this case? Right, so what is the distribution, underlying distribution of this? Right, so this is an empirical distribution. It's coming from data. But what is the underlying theoretical distribution from which this data is coming from? But we don't know, right? Could be. If I impose a normal distribution, and I will apply maximum likelihood is telling us, let's assume a distribution and let's apply the data to it. That's what we get. Is it correct?
No.
It's not, right? Because obviously the data which is underlying was not drawn from a normal distribution. Because the normal distribution should expect to have fewer observations at the extremes. In this case, this distribution is compressed. But also there is not symmetry. Right? So it's very asymmetric. So it turns out that this distribution was extracted by from this. This is a more complex distribution as compared to very simple normal distribution. Now, how do I determine whether one is correct or not correct, and how do I proceed in estimating this? So that's what the maximum likelihood is doing. Now, estimating distribution like this, it's not something that interests us, but what we want to know is to know how does this distribution change when x change. Okay, that's our objective. Remember that this was the major objective of microeconometrics approach. So I want to know how the full distribution of a variable changed when x changed. And what we said up to now, we cannot do it because we have too many unknowns. Okay, so what we are doing in ULS, instead of estimating the effect on the distribution, we simply choose one element of the distribution, the first one, the other. So in this case, let's consider again a conditional test. We want to know how the distribution, as we said in the simplest case, where we have x1 and x2 or x0 and x1, then f distribution of f y condition on x. As we said, it would be something like this. Okay? The two distributions are different. Here we only have two cases. Easy to determine. So we want to know, if I go from here to here, how this distribution change. And we said ULS cannot do this. Okay? So ULS just focus on comparing the averages, comparing new ones. Okay, so how does the maximum likelihood is dealing with this? Maximum likelihood approach is very straightforward. Is telling us, step one, I want to know where this data is coming from. What is the underlying distribution? So the maximum likelihood always assumes what is the distribution that is determining this. So remember, the problem was that I have too many unknowns. I don't know what's the distribution. I don't know what's the parameters. So combination of distribution and parameters can give, for many different combinations, the same data. Now, the maximum likelihood removes one of the unknowns. It says you need to assume what f is. That's what maximum likelihood. Now, if you know that this data is coming, let's assume it's image, is coming from a normal distribution, okay, so this is going to be a normal distribution. F will be a normal distribution. So the maximum likelihood maximizes this function. It maximizes the probability of observing a certain data set as extracted from an assumed distribution. So it says, if this data is coming from a normal distribution, right? So I know the function of a normal distribution. So I'm saying, if x is 0, what is the probability of observing this? Okay, so this is going to be f of y equal, say that this is a equal y equal a, conditional with x equal 0. If I know what f is, which is assuming it's a normal distribution, then I just need the formula of the normal distribution, and this is going to tell me what is the probability of observing this specific value once I have x equal to 0. Now, I can compute this for every element of my data set. I may have people with low 0, x equal to 0, and low versus iy, and x equal 1, lower I. So for each of those individuals, I'm going to have an f, which is telling me what is the density of the normal distribution, in this case, for that combination of data in the data. Now, the maximum likelihood wants to maximize the probability that you observe that sample, which means you want to maximize the product of each individual probability, which is written here. Okay? So we want to maximize the probability of observing a specific sample as drawn from a distribution. Now, the easy one to see is this one, right? So I know what's the normal distribution. How do I maximize the probability of observing this specific sample? Well, then I know that the average is equal to 0, and sigma squared is equal to something that determines the variance of this. That is going to give me maximum likelihood will maximize the probability of observing that. Then, notice, you know how it's a normal function of a normal distribution. It's a very long, complex function. Right? So imagine having a sample of 1,000 observation and writing an objective function that is 1,000 times the product of a normal distribution. Okay? You will need a lot of paper to write it down and a lot of time to compute derivatives. Okay, so how do you solve this in the maximum likelihood? Step 1, you take logs. Okay, so you take logs because several functions, they become linear when you take logs. The normal distribution is one of those. So if you take logs of normal distribution, the problem will become much simpler. In particular, it will become linear. You go from products to a summation, which will make things much simpler because you can separate problems. Right? So if you have a product of many normal distribution, you know that now if you have a summation, then derivatives becomes much simpler because you know that the derivative of products are much more complex than the derivative of a summation. Now, you have this problem here, which is now a maximization of something that is linear. And step 2, you take the M estimation principle. What is the M estimation principle? You just apply what we've just seen. In this case, it's a maximum. So we know that the M estimation principle applies to minimization of a function. Therefore, what do? You put a minus in front. Okay, so if you put a minus in front, this problem here becomes a minimization of the function that is a mix of theta and parameters, which is exactly what we wrote here. It's exactly the same. It's between a minimization of something that is a mix between data and parameters. Okay, so forget about this. Maximum likelihood works. We will have to assume that we can compute first derivatives and that you're going to have a unique solution. Now, just to give you an intuition about unique solutions. if you are estimating maximum likelihoods here, how many parameters do you have to estimate in a normal distribution? 2. The mean and variance. That's how you need to know to draw this function, which means that the normal distribution has 2 parameters. Now, this is a mixture of normal distribution. What is a mixture of normal distribution is a weighted average of 3 normal distributions, which you can see here. One here, one here. Each of those has a weight that sum up to 1. So which means that I'm going to have 2 parameters for this one, 2 parameters for this one, 2 parameters for this one. It's 6 parameters, plus 1 weight for this one, 1 weight for this one, and the other is 1 minus the other 2 weights. Which means that if I want to estimate this, I have 8 parameters to estimate. Which means that I go from 2 first order conditions to 8 first order conditions, right? Which becomes a large number of secondary units. Which means that this is a very complex problem as compared to this one. But it also means that solving for minimums is highly possible that this problem here has multiple solutions. That's the issue here. So simple problem of minimization problem, you saw the OLS, it's a very simple one. You're gonna always find the unique solution if the assumptions are valid. And so the no perfect linearity assumption guarantees that they have a single solution. Now in the maximum likelihood, because things are very flexible and the problems can become easily very complex, if you have very complex distributions, you might incur a multiple solution. Normal distribution is the simplest one. 2 parameters, I got the full distribution. If you use logs, everything will become linear and will be very easy to estimate. Okay. Just one parenthesis here that we're going to see a quick example. Maximum likelihood is very powerful for testing because it based on problems. It is based on minimization problem, which means that for each data, even if I assume one distribution, I can have many potential problems. Because I might say that this distribution depends on x and x1 and x2, or many x's. And that means that I can write problems that are unconstrained. Maybe my y is a long list of x's. And problems that are constrained, which means that there are problems where I impose that some parameters have some values. The simplest one, which is what we do in the OLS, is to assume that some of these are 0. We will see an example. So this is very powerful because the maximum likelihood, which is here, has a precise interpretation. What is the probability of observing the data as extracted from a distribution? Which means that if different problems, different models, gives me exactly the same probability, it means that one is the same of the other. Okay, so in this case, if the unconstrained model, which might have many axes, and the constraints that only has one axis, for example, they deliver the same probability of observing the data, that it means that all other axes must be 0. They must not matter. They don't bring any other information as compared to that. Okay. You can see this as an example, if you want to do it as an example to see what's happening. So this is assuming that y is normally distributed here, and I want to estimate the underlying distribution. This feature, at least in Stata, is already imposed in the software. So if you add the option normal to the histogram, it will plot the maximum likelihood estimation of the data as if those are drawn from the normal distribution. Yes, it's already automatic. And the reason being is that it is particularly simple, because if you try to derive the maximum likelihood solution for this first order condition of the problem we just seen, what are you going to get? What is mu? Mu is the sample mean. Right? You're going to find out that the big solution to that problem is just the summation of x divided by n, the sample mean, and the estimate for the variance is the sample variance. These two elements allows me to estimate the maximum likelihood distribution of one value. Okay, so this is an example of what we got in that case. Right? So if you write normal, you're gonna get this.
More or less.
But in the sample, because the sample is not large, you see that the two are not exactly the same. So if you increase the sample, 100,000, you see that the maximum likelihoods and the original distribution from which the data drawn are exactly the same, right? The two colors are exactly the same. Now, shorts, and here we close. And here we close. Let's see a simple example, which is the OLS. So how do we write the OLS in a maximum likelihood case? So remember, maximum likelihood always has distributional assumption. So when you read the problem and you see, oh, be careful because the error term is distributed in some way, then that should ring immediately a bell. This is going to require maximum likelihood. And the reason is the following. So this is our equation. OLS does not say anything about the distribution of anything. So we don't assume the distribution of anything. But if we want a maximum likelihood correspondence to this, then what we can say is to assume that the error term has some distribution. In this case, the simplest one is to assume that the error term is normal 0 sigma squared. Okay, so the error term will enter in this formula here. Right? So this is the formula of the normal distribution, where you have beta, average, and variance. So the average of u is 0 by assumption. U will be here, and this will be the variance of u. Which means that if you assume that u is like this, then we know the distribution of u, which is this one. This is exactly a normal distribution, where u is defined by this function there. The average is 0, and sigma squared is something that I can estimate. That means that in this case, I just can apply maximum likelihood, and I can recover alpha and beta under the assumption that the error term is normal. Why would I do that? And then we close. Why would they assume normal distribution for u? And what would be the consequence? Why would they do that?
One of the assumptions of the linear always irrational.
No, we said the OLS is written there. Does not assume anything about the distribution of the error term. That's a mistake to say that the error term is assumed to be normal distribution. OLS does not do that. The normal distribution of the error term is a result of large samples, but it's not an assumption we made. Now, if we made that assumption, why we would make it? What's the consequence of going from a case in which we don't say anything and a case where we say something? Yeah, simplify it. So in some sense, we get rid of uncertainty, which means that if we assume that the error term is normal, everything is going to be more precise. Right? If because I got away parts of uncertainty that I had. So if I say, careful, the error term is normally distributed with average 0 and sigma squared, you see this is almost stochastic. Right? So the error term has a constant dispersion. This is giving the problem a lot of information, right, that we didn't have. Before, the error term didn't have to be any distribution. We just needed to be on average, not correlating with x. That's how we assume to be on x. In this case, if we give it this additional information, we want to do it because we are sure about it, and we can improve on precision. But the reality is that u is unobserved. So assuming that u is normal is not required. It's not something we want to do if we don't have to. But we can do it if we want to do that. Now, we close here. Keep in mind that every time that there is a distribution, we're going to apply maximum likelihood. So from tomorrow, we're going to see cases in which we set a problem, and that problem is going to give us some distribution, and given the distribution, we will apply maximum likelihood. Because maximum likelihood, as I said, is a very powerful method that tells us if we have data and parameters, and we know what's the distribution, where this data is coming from, then we use maximum likelihood. Right? So we assume distribution, we minimize the minus of the log of the function, and first order condition gives us parameters, first order and second order derivatives gives us precision, asymptotic distribution. Okay? Any questions? All right, so tomorrow we look at binary outcomes, which will apply a lot of maximum likelihood. The day after, we're going to look at selection.